Okay, thank you. Good evening. As usual, everybody's at the back, so I'll have to shout a little. That's part of my introduction anyway. 22 years in the Royal Navy plus 13 in the Fleet Air Arm. And during that time I spent a lot of time teaching meteorology and oceanography to our naval observers and forecasters, which is where a lot of this comes from. So, you have to excuse me, I'm not used to presenting in a lecture hall before because I'm a simple boy from Cheshire. But we'll give it a go. What we'll be covering is a little bit of history of sound in the sea, physical oceanography, the properties of seawater and how they affect sound, sound transmission, some typical sound speed profiles and examples of sound transmission. We'll look at ambient noise and reverberation at the end. Very difficult to know how to pitch it, whether to go extremely scientific or because I couldn't do that anyway, or keep it very low, which is my area anyway. So if there's too much, then please ask questions. If you've got any burning questions as we go through, please dive in. Otherwise, there should be time at the end for questions when we wind up. Okay, so we start by looking at the history of sound in the sea. How did we get here? So the science of underwater acoustics almost certainly began in 1490 with our friend Leonardo, who wrote, "If you cause your ship to stop and place the head of a long tube in the water and place the outer extremity to your ear, you will hear ships at a great distance from you." That's probably the first recorded recognition that sound actually propagates underwater, although cetaceans or marine mammals have been doing it for many, many years quite successfully. We move on. In the latter half of the 17th century, Sir Isaac Newton published his famous work, Principia Mathematica. Bit of a page turner, but it basically gathered up all his mathematical knowledge into acoustic models. Newton thought that he thought that he correctly predicted the speed of sound through various mediums, either solid, liquid, or gas. And he figured if he knew the density of the medium and the pressure acting on it, or acting on the sound wave that transmitted through, he believed he could work out the speed of sound in that medium. However, he just missed one vital thing out. Latterly, a Frenchman reworked his formula to include the effects of heat on the result, which Isaac had overlooked. As always, you have to have an equation. Did I say there was a quiz at the end? So if you want to make notes, please do. So we move on. The next major step in the development of underwater acoustics was made by Daniel Collison, a Swiss physicist, and Charles Sturm, a French mathematician. So mathematics comes into acoustics quite a lot, as you can see. In 1826, on Lake Geneva, they measured the elapsed time between a flash of light, obviously on the surface, and the sound of a submerged ship's bell, using an underwater listening horn, and that was over about 17 kilometres. They measured a sound speed of 1,435 metres per second, and that was the first quantitative measure of sound that had been done, and it was within about 2% of what current values are recognised to be. You can't go anywhere without having a reference to the Titanic. You've got to have it. The sinking of the Titanic in 1912 provided the impetus for the next wave of progress in underwater acoustics. Lewis Richardson, an English meteorologist, yeah, we like meteorologists, patented a design for underwater echo ranging device for detecting icebergs. Sadly, it was about 2 months too late. The first working sonar ranging system was designed and built in the United States by Canadian Reginald Fessenden, and that was in 1914. The Fessenden Sonar was, I have to say this slowly, an electromagnetic moving coil oscillator that transmitted a low frequency noise. So it transmitted it first, then switched on to receive the echoes back. And that was the first actual operating sonar. It was able to detect an iceberg underwater about 2 miles away, but it couldn't actually precisely detect the direction. So you knew it was there, but you didn't know precisely where it was. Okay, in the UK, the work on acoustic submarine detection was done under the auspices of the Anti-Submarine Division of the Admiralty, or ASD. And therefore techniques became known as ASDICs, or ASD-ICs. But apparently, in order to maintain the secrecy around the work that they were doing, any inquirers were told that the term ASDIC stood for Anti-Submarine Detection Investigation Committee. And we all know how quickly committees come to conclusions, very slowly, so it was meant to put people off. It's actually now apparent that no such body ever existed, so there was no ASDIC division. And during the period from the end of the First World War to the end of the Second, the term ASDIC was used as a word to describe active sonars in the UK. The Royal Navy remained in the forefront of development during the interwar period, and the first operational ASDIC system was set up on HMS Antrim in 1920. And no, I didn't serve on Antrim in 1920. An ASW school was established at Portland in 1923 to train operators as more ASDIC sets were fitted to more ships. Worth noting that the US Navy didn't test its first military sonar until about 1931, so late as usual. It's just a note about HMS Osprey was the school down in Portland, which is sadly no more. The use of echo ranging sets that were now being used showed evidence of a mysterious effect in certain conditions. This became known as the afternoon effect, and it's a recurring theme to talk about the afternoon effect as we go through. And that was thought at the time to be temperature based. In 1936, I have to keep up with my slides. In 1936, this chap Spillhouse, Athelstan Spillhouse, joined the Woods Hole Oceanographic Institute over in the States, where he developed the bathythermograph, or sometimes known as a BT. And that was used to take measurements of ocean depths and temperatures from a moving vessel. But although we said it was a moving vessel, the vessel had to become stationary to take the measurements. So it could move around the oceans, obviously, but needed to be stationary to actually do to take the measurements. His bathythermograph was a small torpedo-shaped device, as you can see there, that holds a temperature sensor and a transducer to detect changes in water temperature. And it measures those against depth down to a depth of about 285 metres. It's lowered on a small winch from a ship into the water, and the BT or bathythermograph recorded the pressure and temperature changes on a coated glass slide as it drops through the water. While it's being dropped, the wire is paid out on a spool, so it's got a drum on board, so you're letting this thing down over the side. It reaches a certain depth, then a brake's applied, and then you've got to draw the whole thing back up on board the ship. We have something similar today for doing what we call CDT drops, or conductivity, depth and temperature. And again, the ship has to be stationary, so it's not particularly convenient to do it. And because pressure is a function of depth, the temperature measurements that it takes could be correlated against depth when they were recorded. So throughout the use, mentioning that it's deployed from a ship, from on a drum. Throughout its use, the various operators and oceanographers noted how dangerous it was. If you imagine the ship heeling and rolling, then it's not going to be a very good place to be when you're trying to lower this thing over the side. And it's fairly common to see your mates on the winch disappear as a huge wave comes crashing over the side. So not exactly a very pleasant thing to do. After witnessing firsthand the dangers of deploying and retrieving these BTs, or bathythermographs, James M. Snodgrass, no, I didn't make it up, began developing expendable bathythermographs, or XBTs. And in the early 1960s, the US Navy contracted Sipican Corporation of Marion in Massachusetts to develop further this XBT. And they became the sole supplier of these XBTs throughout the world. In fact, during my time in the Navy, Sipican, the American Sipican, was supplying these to the Royal Navy, and they were, and as far as I know, still are the sole suppliers. The probe itself falls freely at 20 feet per second. There's a lead weight or a brass weight on the end, and it provides a temperature depth trace to a recorder which is back on board the ship. There's a pair of copper wires, very fine copper wires, which pay out from both the shipboard end and also the end that's free falling through the water. And that copper wire provides a data transfer line back to the ship and records on a graph. So as the thing goes down through the water, it records immediately on board the ship and gives you a trace of temperature against depth. Eventually the wire runs out and breaks, and the whole thing sinks to the seabed. And you may ask, how many of these things are there on the seabed at the moment if we're dropping them over the side all the time? In 2013, globally, there were nearly 36,000 XBTs launched by the major maritime nations, some of them for scientific reasons and quite a few for military purposes. Nice picture of a young lady dropping our XBT. So this is a handheld launcher, and effectively this is a plastic tube that sits inside with a cap on the end, and that is the release pin. We used to have great fun on board ship when the stokers came up, and they'd say, "What are you doing?" "Well, I'm just about to fire this XBT." You have to stand back, fingers in ears. And effectively all you're doing is pulling a pin out, and gravity lets it fall over the side, which is what's happening here. The little black knob you can see there on the end engages as contacts through there at the top, makes an electrical contact all the way through to the recorder on board the ship, and as you pull the pin out, that thing drops at 20 feet per second. And as I said, Sipican still the sole suppliers as far as I know, so if they ever go bust, we won't be doing any more XBTs. Okay, still looking at history. Don't know how many of you might remember this. In the 1960s, we first heard about a nuclear-powered combat submarine which was built for speed and manoeuvrability. Actually, looking at some of the faces, you may not remember this. You probably weren't around at the time. It was the flagship of the, get this right, flagship of the World Aquanaut Security Patrol, or WASP. And it was responsible for policing the Earth's oceans. And if this works...
Stand by for action.
No sound. Remember? Hands up who doesn't remember. Could I just say, I was actually madly in love with the puppet that plays Aquamarina. Not something I could probably admit to these days. Yeah. Okay. It's probably a little bit trivial, that, but it was actually the first common recognition of underwater acoustics. We had a puppet in there called Phones, and he used to listen to sonar on a headset. You won't remember. Look it up on YouTube. I'm sure you'll find it. So that's the history. Has anybody got any questions on that I can answer on the history of oceanography so far? Good. Moving on. There's one last one that I think I must have missed there. There we go. And it's actually quite an important one, this, for oceanographers around the world. Possibly because of their submarines were inferior to many of the NATO boats, especially in terms of quietness. The Soviet Union put a massive effort in providing them with the best environmental support, as in gathering data about the oceans. And from the 1960s through to the fall of the Soviet Union, large numbers of oceanographic research vessels were deployed around the world's oceans. The data collected by these ever-present vessels, along with the fruits of an intensive and sophisticated underwater acoustic research program, was intended to give Soviet submarines the edge over their NATO counterparts. And I do remember being at sea, and anybody else who's been in the Navy will do too. You always used to see these little survey vessels popping up, big radars on the top, big antennas, but they were actually gathering oceanographic data from around the world and mapping the oceans. And the atlases that the Russians put together were really, really very good oceanographic atlases, and we still look to use them today. But yes, certainly they weren't only gathering oceanographic data, they were doing the sneaky beakies and listening to what we were transmitting as well. In fact, a senior Soviet admiral, one Rear Admiral Anatoly Rosoko, is quoted as saying in 1973 that it is my responsibility to ensure that every Soviet submarine understands the ocean and how to hide in it. How many people saw The Hunt for the Red October? It's not as far-fetched as it looks, it really isn't. And there was a joke that the Royal Navy were using that as part of their training videos. It wasn't a joke. It really was used. So that's the end of the history bit. Any questions? Right. I'll look now at physical oceanography. So we know how there's been lots of research done. But how does all this affect acoustics? Well, there's three basic properties that we look at in the oceans: temperature, salinity, and depth or pressure. And all of these influence density, which is what affects the sound speed in the oceans. So it's density that influences the speed of sound in water, but it's those three elements that affect the density of the ocean. So we're going to look at each one in turn. Hope not to spend too much time on them, but it'll give you a flavour as to how they actually affect the density. Okay, seawater can exist in liquid form at a temperatures of minus 1.8 degrees Celsius. And this is because of the dissolved salts which interfere with the formation of ice crystals. And Martin mentioned that I used to serve on HMS Endurance down in the Antarctic. And the one thing that really threw me was going down towards the ice, expecting the temperature to get to zero and freeze, but the sea temperature kept going down and down to about minus 1.8, and I thought, I'm there checking all the instruments. Is it right? Can't be right. But yes, you can get temperatures down to about minus 1.8, and I'm sure I measured minus 1.9 at one point. Obviously, water temperatures as low as these are found only in polar regions and at great depths. The warmest surface waters are in equatorial regions, that's fairly obvious, and can reach up to about 30 degrees Celsius, which is a nice warm bath.
It's warmer than that in the Persian Gulf in summer.
This is generalisation. You can get, obviously, spot temperatures a lot higher. Because the influence of weather conditions, the greatest variability in temperatures occurs near the surface layers. Where's my stick gone? Near the surface layers. And these layers tend to be fairly well mixed by weather influences, and they vary in depth with latitude. So you can see in the temperate latitudes we've got a deeper mixed layer. At depth and away from these weather conditions, the waters are nearly all isothermal, and for those that struggle with that, we'll look at what isothermal is a bit later on. Separating the two extremes of water is an area known as the main or permanent thermocline, which is this thing here. So mixed layers at the top, deep layers which are fairly constant in temperature, and then between the two, a main thermocline. And a thermocline is a zone where temperature varies with depth. So from this layer, the temperature is going to drop off and have a negative temperature gradient down to that deeper layer. It's normal for thermoclines mainly to be negative. Obviously, the temperature is decreasing. But you can get positive thermoclines around the globe where you've got salinity at depth. And I'll show a few examples of that a bit later on. Just repeats the lesson, I think. The main or permanent thermocline is always present in deep waters between about 60 north and 60 south. Other thermocline layers can also exist within that mixed layer at the top, and again we'll cover those shortly. This whole thing is described as a three-layer model. So for the quiz, three-layer model, all right? So looking at thermoclines, as we said, other thermocline layers can exist within that top thin layer, and one of these is known as a seasonal thermocline. It's a negative thermocline which subdivides water between the lower levels and water near the surface that's been warmed up by the seasons. That's why it's called a seasonal thermocline. So you have a seasonal timeline from winter through to summer, and the waters will gradually get warmer and warmer, obviously, but that introduces a thermocline near the top layers. So that thermocline starts in spring, increases and becomes more active in the summer, and then declines through the winter. Our transient thermocline, a bit more interesting, I suppose, because it comes back to the afternoon effect. Remember we mentioned the afternoon effect earlier on? Something that had been discovered and weren't quite sure what was causing it. So near the surface, top 10 metres, and certainly above our seasonal thermocline, we have another layer which gives us another temperature gradient. Quite short-lived, it can last between a few hours or a few days. And this graph, he says, hopefully, that comes on, breaks down those thermoclines. Again, transient one quite near the surface, you've got a temperature falling off with depth down to about 10 metres. Then we've got temperatures fairly constant. Then a seasonal thermocline coming down a bit further, then constant again. And then we get down to really deep waters where we have our main permanent thermocline between surface layers and our deep water, which is all at one temperature. So looking at the transient thermocline, let's put it all up. How does it form? It forms, as I said, it's above the seasonal bit, it's short-lived, it needs an air temperature, it's almost like it's alive. This transient thermocline needs an air temperature greater than the sea temperature. Very little cloud cover, very light winds, and a high solar elevation, as in it's in the afternoon, hence the name afternoon effect. That's mainly when you'll see it. It does tend to degrade sonar performances, as in you'll get very short ranges or no ranges from your sonars. And I don't just mean Navy sonars, it could be an echo repeater, it could be fish finders, side scan sonars, trawl sonars, underwater telephones. But the Navy are quite worried about it because it means you can't see your Soviet submarine. On a daily basis, what you'll get is 7 o'clock in the morning, maybe 20 degrees at the surface. This is our surface layer here, and as the day warms up, you can see that a layer develops near the surface, and this is going to affect our surface mounted sonars all the way through to the afternoon to about 1700 when that's the worst case, and then it starts to cool off again, and it'll eventually come back round to our early morning values. Although I said it lasts for a few hours during the day, it can last for a few days or even up to a few weeks if the conditions are so stable and don't change. There's no mixing of that surface layer. That's temperature. One of the other things that affects density of the water and therefore affects sound speed is salinity. The most commonly used term to describe saltiness of the ocean is salinity, although halinity is sometimes used because the bulk of the dissolved salt is sodium chloride, which is a haline salt, but we all talk about salinity. In oceanography, it's been traditional to express salinity not as a percentage, but we talk about it as parts per thousand, or PPT. And what that represents is it's approximately the grams of salt per litre of solution. So when we talk about salinity, we're always talking about 37 parts per thousand, or 35 parts per thousand, a number, parts per thousand. Values there that we can see, the range is approximately 33 to 37 parts per thousand in open waters. The highest value that I've come across is probably slightly more than 37 parts per thousand, but high values will be found between 20 and 25 degrees of latitude, both north and south. You'll find it in eastern Mediterranean at the surface and also in the Dead Sea. Eastern Mediterranean is probably quite a good one to mention there because of the gyre of the Mediterranean over in the east, you get maximum insulation over there and evaporation. So the water's evaporating, so the Mediterranean Sea in that area gets quite salty. The more salty it gets, the denser it gets, so it will then sink to a lower level in the Mediterranean. And because of that gyre, that salty, warmed water will move towards the outflow of the Gibraltar Straits. And when it hits the Gibraltar Straits, it's still dense. It'll spill over the Straits of Gibraltar, down into the Atlantic, and you've got a body or a balloon of warm water down at depth, which is warmer than the water above it. So therefore, that's when you get a positive temperature gradient. So if you go diving to the west of Gibraltar, you'll notice it'll get quite warm as you go further down. Variations with depth. Top 1,000 metres are the most variable, as we were saying, but below 1,000 metres it's almost constant in open oceans at 35 parts per thousand. How does that compare? Well, fresh water, about 0.5 parts per thousand. As you get closer to the sea, you'll get up to about 30 to 33 parts per thousand, and then into the oceans, 35 parts per thousand. Temperature, salinity. The third factor was pressure or depth. Fairly simply, the water pressure is the result of the weight of the water above it. That's fairly obvious, I think. And that's the reason why water pressure increases with depth. And the pressure only depends, and again this is fairly obvious, but the pressure only depends on the water above it. It doesn't matter where you are in the world, the water pressure at depth will always be the same at that depth, whether it's the Arctic, the Antarctic, or the middle of the Atlantic. And it'll be the same pressure at that level in all directions. So as we've said, factors affecting the speed of sound, or how fast sound travels underwater, is density. And density is determined by those three factors there: temperature, salinity, and depth. So how do they actually affect sound speed? An increase in density causes an increase in sound speed. So you get the density to increase, sound speed increases. And those changes in density are caused by a fall in temperature. So a 1 degree decrease or increase in temperature results in a 3.6 meters per second decrease in sound speed. Decrease in temperature, decrease in sound speed. Density of seawater is proportional to its temperature, but the opposite is true for salinity and depth. So a rise in salinity. If you get a rise in salinity of 1 part per thousand, the sound speed, or the speed of sound through water, will increase by 1.4 meters per second. Increase in depth. For every 100 meters you go down through the water column, you get an increase in sound speed of 1.7 meters per second. So of those three, you can see that temperature changes, or changes in temperature, offer the greatest change in sound speed. The least is salinity, and the second highest is depth. Approximate sound speed values in water tend to be between 1430 and 1560 meters per second. So, how does this affect ASW applications? There's a few different countries around the world that have got different ways and means of using this knowledge that they've got. In North Korea, I'm glad you like that because there's loads of those. So that's the properties, the physical properties of the ocean. Temperature, salinity, and depth affect our density and therefore affect the sound speed. So we've looked at history, looked at physical properties, now we're going to look at actual sound transmission in seawater. And I think you saw at the beginning there was 832 slides. This is about, I think we're up to about slide 47 now, so just a few more to go. So what is sound? Sound is created by a vibrating object and has a longitudinal oscillatory motion of water molecules. And sound propagates by exchanging the energy between each molecule and velocity and displacement, as it says there. Acoustic sound energy is the best medium to detect an object underwater. This is what we found. This is what Leonardo found. This is what Newton was modelling as well. And it's because sound energy will travel relatively long distances underwater, and in some cases this can be kilometres. Radio or radar doesn't travel particularly far, and light waves only travel short distances and are measured in metres rather than kilometres. we all know this because you look into the water, you look down, you can't see very far, can you? You can see a few meters of depth, and then after that you can't see anything because the light won't penetrate. But sound will transmit long distances. So sound, let's get the other one up as well. Sound can be thought of as a series of wave fronts. So if you drop a pebble in a pond, you get ripples moving out from where the pebble went in. That's our sound source, and those waves or wave fronts move out from that pebble dropping in the pond. But for analysis purposes, it's convenient to think of sound travelling out in rays, like these things here. So although we've got a wave front of sound moving out from our sound source, we actually describe the sound path as a sound ray moving out in a certain direction. So using the idea of rays, it's possible to illustrate a sound path by a single line between a source, maybe over here, and a receiver over here somewhere. So what we'll start to look at is how the sound path or the sound ray looks through the water column. Bit of a simulation, I hope, if it works, to show it does work. Our longitudinal wave, like slinkies, like them going downstairs, really good. So nothing actually moves apart from the energy being transmitted along that slinky wave. Okay, so we've got sound moving out. It moves out in waves. It's described as a ray. What happens to the rays? They can refract. So what is refraction? Refraction is a change of direction, and refraction of waves involves a change of direction as they cross a boundary. And these rays will then bend as they cross a boundary, and the boundaries will be changes in temperature, changes in depth, changes in salinity. Okay, in practice, sound rarely travels in straight lines like I showed there. It's a shame that. And there can be multiple paths connecting any source and receiver. The variations in temperature and salinity and pressure in the water column cause the speed of sound at which sound travels to vary. And it varies, as we said before, by 3.6 metres per second for temperature down to 1.4 for salinity. Variation of sound speed from place to place in the ocean causes the rays to bend and follow curved paths. And this bending is known as refraction. One thing to note is that sound always bends from a high sound speed value towards a lower sound speed value. So as your sound is transmitting, propagating through the ocean, it will always try and bend down towards the lower sound speed. Looks a little bit like this. So say we've got a layer in the surface with a high sound speed value, typically 15-25 meters per second. Below it, for whatever reason, we've got lower sound speed values of 1490. So our sound rays, if that was the direction of the waves, they would be bending towards the lower sound speed. This will become clearer when we look at more, well, not complicated, but we'll look at the paths more fully. So, right, looking at sound speed profiles. This is what we talk about the rays and the way they look between source and receiver. This is a sound speed profile and sound transmission path. Okay, so although it's given as a function of depth, the sound speed value is only a value at a certain depth. And that value, whether it's 1520 meters there or 1535, it's got that value because of the temperature, salinity and depth, and how that's affected the density, and that density then affects the sound speed. So from this, I mean, this is showing a profile, a sound speed profile, down to a depth of 2,000 meters. And looking at the shape of it, you can see how the effects vary with depth. So at the surface, our temperature is causing a rapid decrease. Temperature is decreasing, so that's causing a rapid decrease in the sound speed. As you get much deeper, that temperature gradient becomes less, but what takes over is the effects of depth and pressure. So the depth, therefore the pressure, is increasing with depth, so that's now starting to cause our sound speed to get higher. What you can also see in this profile is something that's known as a sound channel. So when the value of sound, or sound speed value, reaches its minimum, this is what we call the sound channel axis. And if you had a transmitter stuck down there about 200 meters, any sound being transmitted from that would transmit horizontally and quite for long distances, because you're making the most of the profile that you've got there, and it will trap sound in that sound channel. Again, looking at other ASW applications, Russia, any ideas what their applications might look like? I'm sure it's Soviet, because that looks like a Soviet uniform to me. Not that I've seen that many. Okay, transmission paths. It's only another 572 slides to go. We're doing all right. I'll look at some descriptive terms for sound speed profiles. So sound speed structure of the ocean is largely determined by the temperature structure, and in the majority of cases salinity variations we ignore, and we then look at depth as the overriding factor in deeper water. There can be an infinite variety of temperature profiles found in the sea. Most of them can be related to a number of basic types, and this is what we start talking about, different types of profile. In temperature, we talk about isothermal, mentioned it before. Isothermal, no change in temperature with depth. A positive temperature gradient, fairly rare. We mentioned it briefly about the outflow from the Gibraltar Straits, where the temperature at depth is greater than it is at the surface. Not that many areas of the globe that exhibit that type of gradient. Normally it's a negative temperature gradient where the temperature falls off with depth. It's what you'd expect. We also have some descriptive terms for sound speed. Isovelocity. Any clues? Constant sound speed with depth. Positive sound speed profile is where the sound speed as you go down through water increases, or negative sound speed profile due to decreases in density with depth. I mention those because in describing the ray paths and the ray diagrams, it's easy to talk back to these things and explain why they're valid for certain occasions. So a ray path is defined by its sound speed gradient. Sound rays, as we saw with the pebble in the pond, are a function of, we've got the wavefront going out, but the sound ray itself is the path that the sound takes. And the sound speed gradient defined by temperature, as we said, in the upper levels. So looking at the first one, isothermal, where there's no change in temperature, the only changes that we'll notice are changes in pressure or depth, and that's the dominant feature. So sound speed will increase with depth, marginally, and it will produce a slightly positive sound speed gradient. So sound, which is always going towards the lower values, will generally bend upwards. It looks a little bit like this, where we've got a sound source near the surface there, the temperature gradient, temperature doesn't change with depth. So the only thing that's changing is the depth itself. So that's causing the sound speed to increase with depth. And our sound source here, the ray of various rays from this sound source will always slowly start to bend back upwards, because the sound speed is lower at the surface than it is down here, so it's trying to bend back up towards the surface. If we had this positive temperature gradient, where we've got an increase in temperature with depth, I'm using the outflow of Gibraltar, so you've got an increase in sound speed with depth. You've also got depth causing the sound speed to increase. So what happens is that you have a profile that looks like this. So we've got a sound source there. You can see that temperature is increasing with depth. So our sound speed will increase rapidly with depth, because you've got two things acting on it, temperature and depth itself. So any sound you transmit into the water will try and bend back up rapidly. Our negative temperature gradient. It's a decrease in temperature, and sound will bend downwards because temperature is decreasing, so the sound speed is decreasing. So any transmissions are all trying to bend downwards, and this is where you end up with this thing called a shadow zone, which is what our Russian friends are trying to find by knowing all about the oceans. So when you've got a shadow zone like this, all the sound is being bent downwards, so you can't hear or see anything in this region here. And as the Russian admiral said, if he understands the oceans, he knows where to put his assets. But in practice, it's never as simple as that, obviously. You get a mixture of all of these things, and you get some very complicated ray paths. So, an isothermal layer at the top, so we've got a little bit of bending. Then it goes negative, so it all bends downwards. And I mentioned this isothermal layer, we have what's called a surface duct. And these sound rays that are all bending back upwards will just propagate down this channel. As we said, here the sound speed is becoming less and less and less, so the sound rays will all bend downwards. So we've got a huge shadow zone over here. So again, knowing what your profile looks like, what the oceans look like, this is where the red October would be hiding. One other thing that we should talk about is the Convergence Zone. It's terminology, it's one of the terms we use when we talk about sound transmission. We have a negative temperature gradient near the surface, and you get layers that cause sound to be refracted downwards. The downward refraction will continue to great depths. So if you've got really, really deep water, like in the middle of the oceans, this is where the Convergence Zone pops up. If you've got sufficient depth of water, the rays will then start to bend back up again because of the pressure, causing increasing density, so that pressure will cause the sound rays to come back to the surface. In effect, sound rays become focused in a small annulus, you said annulus, at a distance away from where your transmissions are. This phenomenon is known as Convergence Zone propagation, and as we've said here with Convergence Zone, if you've got sufficient depth of water, and you've got to have really deep water, about 3,000 metres, and it's the effect of the depth which is causing increases in sound speed, which causes those rays to bend back up again to the surface. They'll converge at a focal point, typically North Atlantic, 35 to 40 miles away. You'll have this focus, and in the Mediterranean about 10 to 15 miles. It's a bit like have you been to St Paul's Cathedral in the Whispering Gallery? You sit on one side and whisper to somebody on the other side. That's kind of what the Convergence Zone is like. You can't hear it halfway around. You've got to be in a certain point to get that focal point of the sound. It looks a little bit like this. Really deep water. We're talking 3,000 metres of water. Sound source up here somewhere. Sound's bent down, bent down, bent down. We talked about the shadow zone being there. But then the sound can bend back to the surface and we'll get a convergence zone maybe 35, 40 miles away in the North Atlantic. So effectively, you could be over here. You'd have no contact of anything in this area, but then you'd suddenly find you've got an intermittent contact coming in at 35, 40 miles away. And then you'll lose him again. That's all down to convergence zone, and it's all down to how the rays are being bent back up due to temperature, salinity and depth. Okay, ambient noise. I think we're up to about slide 622 now. Ambient noise is the noise of the ocean itself, and it's made up of lots of different aspects. So this is like background noise. So we have shipping noise. You've got sound from distant shipping can travel as far as 300 miles. Obviously, the closer you get to a major shipping lane like the Dover Straits, the background noise from shipping will be very high, and that will affect your sonar because it's impinging on how you're trying to hear. Wave action. Level of noise produced by waves increases with wind strength. So if you've got high winds, that background noise due to the sea state will be quite high. Rain or hail. The extent and intensity of precipitation affects the level of this background noise. Obviously, snow won't affect it because it's a little bit airy-fairy and won't make any noise on the surface of the water. Biological noise, the sounds produced by marine life. You've got whale calls, snapping shrimps, dolphin whistles, dolphin clicks. All of these affect background noise. Seismic disturbances, earthquakes underground. Then man-made noise. You've got noise coming out of ports where there's piling activity going on. There might be some industrial activity going on. Ice regions. You get icebergs, calving. That adds to the background noise. It's a lovely curve. I love this one. Nuds and curves. I'm not going to go into the curve itself. That's part of the quiz at the end. So just make a few notes as you go through. What this is just trying to show is that that's the level of noise, or the sound level, and this is frequency along the bottom. So we have, what this is showing here, for example, is that different sea states, shown in blue, will give you higher noise levels in the water, up to gale force 8, at higher frequencies, whereas turbulence at lower frequencies. It's just a graph that puts everything together in one place. I'm not going to try and break it all up. Earthquakes have high noise levels, but down at these frequencies, really low frequencies. Also in the acoustic environment, we have reverberation. And there's a lot more targets in the sea than what we're looking for. And all of these echoes, all of these objects give echoes back. And they all merge together to give background noise known as reverberation. Also, in shallow waters, you'll get reverberation as well, with noise bouncing up and down off the surface and also off the seabed. So all of these things add to the complication of trying to listen underwater. How do the Americans do it? The Americans have to be aggressive about it, don't they? So, in summary, this is slide 832. We can say that we looked at the history. Earliest experiments on sound transmission were by Leonardo da Vinci back in 1490. Developments throughout the centuries. We had Newton. We had the sinking of the Titanic, which wasn't necessarily a development, but it led to something. We had ASDIC, which may or may not have existed, but not sure. We had our Russian environmental data capture, sending out ships all over the place. Ocean properties, we looked at ocean properties. Temperature, salinity and depth all affect how sound travels through the water. The temperature gradient, I decided and told you, that it's the most dominant feature in surface layers. But when you get to depth, depth itself is a dominant feature and causes sound speed to increase. The afternoon effect degrades sound transmissions. That's and affects acoustic operations near the surface, and that's caused by our transient thermocline, which is also known as the afternoon effect. We looked at our slinky, how is sound transmitted. It travels as a wave through its medium. We started to get into sound very rarely travels in straight lines, and it's quite complicated and complex. Sound bends from high speed to lower speed. You get lots of complicated combinations, so it makes predicting how far you can see through the oceans really quite difficult. You get ambient noise interfering with it, as well as reverberation, which all goes to prove that actually we're talking about a very inexact science throughout.